Hello, we're going through these little tests. Bear in mind there's two versions of this, and I don't know what version you had. Um, so don't worry if the letters don't match. It's the I will point out what the answer is as I go through it. So this first one, um, the blood vessel carrying a vein which contains oxygenated blood. Well, it's the left side of the heart. So this is the left side. That's the right side. It's the left side, and it's D on this diagram. Yeah, these are our veins coming back into the heart because this is our atrium where I've just put the arrow, and then blood's going to leave via B. That's the aorta. Off it goes over here. Label line again. It needs to touch a semilunar valve between the left ventricle and aorta. So again, it's kind of similar, but it should be a line touching that valve flap, labelled V. Why is that worth 2 marks? So straight line, labelled V, touching a valve flap gets you 2 marks. There's 1 mark if you've got one thing wrong on that. So yeah, you should have used a ruler line touching it. It can't be a curved line or anything like that. I could have labelled the other side of that valve as well. And then we've got the classic. It's amazing how many people got this wrong. It's just the difference. So 780 minus 250 divided by, it's the increase in the rate of blood flow. So it's 250 at the bottom multiplied by 100. Work that out quickly. 780 minus 250 equals 530 divided by 250, which comes in at, multiplied by 100, which I always forget to do. Yeah, that's 212% increase. Sounds a lot, but 100% increase would be 500. So it is a big increase in the heart rate. On to number 5. We're doing well here. I think these are the easier questions on this. Correct about veins. There are no multiple choice on our exams, but I always like tick and cross them as I go through them. Correct. They carry blood at low pressure. Yes, they do. They carry blood away from the heart. No, that's an artery. They have valves. Yes, they do. They have a small lumen compared to, no, they have a large lumen, so it's not that one. They require elastic tissue to help, no, that's the arteries. So yeah, it's A, and C on this example. Again, the letters, I kind of jumbled the options around so that people couldn't moan that, or they could see each other's and things. So it's fair. And then with reference to the diagram of the heart valves, which one of the following is a correct statement about the heart? Well, these are open valves and these are closed. So the valves between the atria and ventricles are open. So if I just push this over slightly so I can get my pen working. So yeah, and remember, systole means contract. You never get a time when the ventricles and atria are both contracting. So systole, that means contract. Diastole means relax. So this is, for these to be open, well then the atria must be contracted because that's when they force these valves open, and the ventricles must be relaxed. So atria must be in systole and ventricles must be in diastole. So it is ventricular diastole and atrial diastole. No, that's relax and relax. Again, they never do the same thing at the same time. There is a slight period of relax. It is ventricular diastole and atrial systole. Atrial, yeah, so yeah, it looks like C is the answer. That's when, these valves are going to be open, and obviously these are closed, so ventricle isn't contracting. I'm just thinking it could be B as well. I'll have to kind of because you do get like the residual pressure that comes into the heart and it kind of dribbles through, and then the atria contracts. So actually, it could be B as well. Need to check that with the rest of the teachers and make sure that we've avoided that. Number 7. Oh yeah, lots of people struggle on this, and I'm going to struggle now because it's oh no, what? Because it's a scale bar. It's the same answer, isn't it? Each time. Oh no, I will. I haven't got a printout of it, and the size of the image is obviously crucial to it. People get confused between image and actual here. This is a scale bar. Obviously, this scale bar isn't 50 millimeters. So this here, that is the actual. The scale bar is the image. Okay, so I measured the image and the actual. I'll do it on my screen version here. It's really not far off. So I've got like 20 millimeters on my scale bar measuring it. It is really 50 millimeters. Magnification equals image over actual. So magnification equals 20 divided by 50. It's an unusual one, is this, because this is smaller than the actual heart. So 20 divided by 50, I've got 0.4. Again, there was one mark for an answer to two significant figures, so I tried to make it so that you had to do it to two fig. But mine comes in at 0.4. The answer is less than 1 because the picture of the heart is smaller than the actual heart. So it's a reduced size image, and you're just not used to them. We are used to having an enlarged picture, and therefore you're used to kind of magnifications being a number more than 1, not less than 1. But in this case, it is. Remember, this answer won't be the correct answer. But when you look at yours, it's have you done it to 2 sig fig? You get 1 mark for that, and you get 1 mark for getting the image over the actual, and the actual is the 50 millimeters. There's no unit conversion, so again, tricky, but they can ask them. Order of blood vessels, leaving the leg, so it's coming back into the heart. So yeah, it must be vena cava first, so that one's sorted. Then we're in the right side of the heart, so right atrium, C. Then it goes into the right ventricle, so that's G. Then it's going to go off to the lungs, that's E. Then it's going to return to the left atrium, which is B, into the ventricle, which is F, and then finally out via the aorta. Again, just learn your heart structure. Number 9, binding 1 molecule of oxygen to hemoglobin makes it easy for the second one to bind. Give 2 letters that are the correct reason for this. A is not correct because the Bohr shift is due to a drop in pH due to more carbon dioxide dissolving, forming carbonic acid or lactic acid formation. Binding of the first oxygen uncovers another heme group. Yes, that's true. Binding of first oxygen allows peptide bond formation. No, that's complete nonsense. It sounds sciencey, but it's nothing. It's peptide bonds are between amino acids. Binding of first oxygen changes tertiary structure of hemoglobin. Yes, it does. Binding of first oxygen causes hemoglobin to denature. No, it doesn't. So this is B and D on this example of the test. It changes the tertiary structure that reveals another heme group. So yeah, B and D are kind of like in the same sentence really for a good answer about how hemoglobin changes its affinity for oxygen. And the advantages of the Bohr shift in humans, hemoglobin has a higher affinity for oxygen. No, it has a lower affinity for oxygen. Increased dissociation of oxygen, yes, it releases it more easily. Red blood cells become more saturated with oxygen. No, they don't. Muscles have a lower affinity for oxygen. No, they don't. Again, that's just like a nonsense statement. Yeah, anaerobic respiration is delayed. Yeah, more oxygen is supplied to the muscles, therefore less anaerobic respiration. So again, it's B and E on this example. Again, they'll be jiggled round on your version potentially. 2 safety precautions. There's lots that you can go for here. You can't have goggles. It's using scalpels, so it's cut away with scalpel. Scalpel. Washing hands afterwards. Some people put before and afterwards, but it's the afterwards is the important one. Washing hands. Disinfecting surfaces. Disinfect surfaces. Safe disposal. A few of you put getting it from a reputable source, which you have my sympathy, but it's not on an AQA mark scheme, I'm afraid. So or not on the one that I checked. But yeah, you have my sympathy. But yeah, you better give the tried and tested ones. There are more flat surface. I'm cutting it into it on a flat surface. Disinfect surfaces, stroke equipment as well. Obviously, that's not 2 marks, but you could have said disinfect equipment. And then we've got the pressure changes in the left ventricle. It takes to show whether the valve is open or closed. I should draw my little heart here. So those are the atria. This is the left side. The ventricle. So yeah, pressure's increasing. It's just about to decrease. So yeah, this is where the left ventricle is well and truly contracting, and blood is leaving the heart. So that means that the semilunar valve that is here, that's the semilunar valve, that must be open. And the AV valve here, AV must be closed. So left atrium, left ventricle, the valve between the left atrium, so that's my left atrium, and ventricle, well, that must be closed. And between the left ventricle and the aorta, well, it's the aorta that's going to be leaving here, so that's our aorta, that needs to be open. They are never ever open. These 2 valves are never open at the same time. When they close, you get the noise of the heart, the lub dup, lub dup, lub dup, and therefore, yeah, when one closes, you hear it when the other one closes. So they are definitely separate. And it's just knowing that what happens in the left side of the heart happens at the same time in the right side of the heart. So it must be tick and tick. And there was basically 1 mark for those 2 and 1 mark for these 2. Again, tricky because it's an unusual way of showing it. So that's outside. Let's go to another one which I probably might struggle with because of, oh no, I should be to this because it's a comparable thing. So yeah, this is testing like a lab skill. So this big scale here, so the big scale here, so that's my stage graticule. That's my stage 1, and this is the eyepiece one. So I can work out that, well, between 4 and 5, each of the small divisions, as it says here, is 100 micrometers. So that's basically 1,000 micrometers or a millimeter. And I know, therefore, that on my eyepiece, 9 divisions is proportional to 1,000 micrometers. So I could say, therefore, that 1 division is proportional to, so from a bad proportional sign, so if I divide both sides by 9, 1,000 divided by 9 equals, yeah, so it's 111.1 micrometers. So that's what I use my calibration one for here. Then this same little scale is here. See, it goes to 8. So it goes 0 is there, 2, 4, 6, so it's 8. So 8 multiplied by 111.1 is 888.9, and therefore the closest answer is E. So yeah, that's the closest one to the answer on this one, E. So yeah, so it's yeah, this is the calibration of the eyepiece. There's quite a lot to do to get the mark, but hopefully that makes sense. Any of these that you think I've no idea what he's talking about, pop along to workshop Tuesday, Friday, and we will help you. 14 is a hard one because it says oncotic pressure, but it defines oncotic pressure. Oncotic pressure is a pressure due to proteins in solution. So this is where I've got my capillary. I've got a pressure pushing out, hydrostatic pressure, and I've got a pressure coming in. That's due to the proteins in the blood. And it's basically, which options A to D would result in the formation of tissue fluid. Well, tissue fluid is outside, so I need more fluid going out than is coming in. So yeah, so my hydrostatic pressure is less than oncotic pressure. No, they're not equal. Yeah, oncotic pressure is less than the hydrostatic pressure, so it's C. Yeah, I need my outward hydrostatic pressure to be higher than the inward pressure. 15 is straightforward. Yeah, is which is showing the aorta where it's got the thickest wall. The biggest number is B on there. It's got the thickest wall. Tissue fluid. This is tricky. Excess tissue fluid is what would not cause excess tissue fluid? Well, high blood pressure does cause tissue fluid because you get more of that filtration. Blockage in veins, yes, that causes like a backup of blood, so you get more pressure, more forcing out. Blockage in lymph vessels causes it as well. Reduction in protein, that also causes, because you don't have the oncotic pressure to pull it back. So it must be E. Yeah, if you're dehydrated, you don't swell up. If your blood's got less water, then more water will go back into the blood. So you'll have the opposite effect of forming tissue fluid. You'll be absorbing fluid from your tissues back into the blood. So yeah, it's E. And then the classic graph, which letters A to D show the point with the semilunar valves. Again, make sense of it first. We'll put my coloured lines on. I'm just going to go over the aorta because it makes me do it. So yeah, so there's my aorta, and that's interacting with the ventricle. So B and C are when semilunar stuff happens. Get a pen that works. So that's semilunar and semilunar. Well, when the pressure in the ventricle is greater than the aorta, the semilunar valve opens, and when it's less than it closes, so it must be C. C is when the semilunar valve closes. That's the valve between the aorta and ventricle, and it closes when the pressure in the aorta is greater than the ventricle, and as you can see in the diagram, that's easily the case. High aortic pressure, dropping and low ventricle pressure. One cardiac cycle. Again, I'm starting at 0 there, so I don't have to worry about 1. It's like, when does it come back to that point? Well, I just kind of, sorry about that. And I'm going to follow it round, and it is exactly there. This is where a lot of you are poor at reading scales. It's exactly that point there. Yeah, and I've been putting on the 0.7 here. So 1, 2, 3, 4, 5. So that there is 0.7. Well, look, it's right between 0.7 and 0.8. It's 0.75 of a second. Okay. So yeah, it's kind of hard to get wrong that if you just take care with the scale. This one's really tricky. Again, some of you managed it, but then read the scale wrong. It's basically this bit of the graph here. Let me get my highlighter. I'll do it in yellow. It's this bit here. It's that line there between A and B. And if we take a reading from it, just get a pen again. So it's kind of, the crossover point is like, it's easily done. Is there. So that's where it starts, and then it ends. Well, it's kind of 2 blocks along. Yeah, if I kind of follow that up to the next point. So it's just 2 blocks on this scale. Well, 2 blocks on this scale is, it's going up in 0.2s. So, sorry, 0.02s. So that's 0. 1, 2, 3, 4, 5. No, that's 1. Sorry, 0.1. And therefore, these small blocks is 0.02. So that's 0.02, 0.04, 0.06, 0.08, 1. I've got 2 blocks, so it's 0.04 of a second. 4 hundredths of a second. Okay, the number of people who put 0.4 of a second, well, you can see 0.4 of a second here, that's up to here. Yeah, so it's obviously wrong. And it's just that little bit there. Pressure's increasing, and then it finally gets higher than the aortic pressure. Therefore, the semilunar valves get flung open. Hard one. Again, I've only bought one class, and no one got that. It makes me think, am I wrong? But I don't think I am. But you never know. And then number 20, which the following will be a correct description if the right ventricle were also shown on the graph. Well, as I said before, the things happen at the same time. Maximum pressure, and the right side is less muscular, so there's going to be less pressure. So maximum pressure would be higher. No, it wouldn't. Maximum pressure would be lower. Yes, and peaks at the same time as So I think it's big, but let's just check. Maximum pressure would be higher. Nope, and peak earlier. Maximum pressure would be lower and peak earlier. No, they're at the same time. It just works at lower pressure. It's pretty cluttered up to death now, is this? But it would look. Let me just pick a really chunky pen so you can see it. It'd look kind of same, and then it'd be just going up to here and down. That's what that graph would look like for the other side of the heart. And then 21. Back to my small pen. And this is just a unit conversion, really. One heart rate. Well, first of all, cardiac output equals heart rate times stroke volume. Stroke volume is 90 centimeters cubed. I need to convert that into decimeter cubed. And 1 dm cubed equals 1,000 centimeter cubed. So that equals 90 divided by 1,000. Can't believe I'm doing it on a calculator, but I do lose zeros for fun. Is 0.09 decimeters cubed. So you get 1 mark if you do that conversion. Heart rate I need when one is 0.7 a second. So 60 divided by 0.7 is going to give me the heart rate. How many 0.7s is the seconds are there in a minute? So that's 85.7. You get 1 mark for that, but you don't get 2 marks for getting both and then getting the rest wrong. So 85.7 multiplied by 0.09 is 7.7. You got that right? I think so. Yeah, 7.7. Sounds about right. Like 7 liters in a minute. Sounds about right. And the number of people who got this wrong was staggering. Again, it's D, plasma, blood plasma. Blood is a tissue made of cells and the fluid it floats in. So yeah, the fluid X is pointing to within where the red blood cells are in the capillary. So it's definitely not tissue fluid. Tissue fluid would be here, outside, surrounding the tissue of the the cells, whatever muscle cells they are. Yeah, so it's just plasma.